We have some friendship. Please,
Here, I touched things like people with the hair.
Happy Thursday. Final two tests. Ratio test and root test. Sure, let's have the test today.
Oh.
Why not? I'm down with that. Means I only have one more week left. I can take the last 2 weeks off. After these two tests, we then look at power series. So next week is all about power series. Right, and these tests are so important because power series representations are only valid for certain intervals. And you have to determine whether the endpoints converge or not, and that's where these tests come in. In fact, we're going to be using the one test we learned today to define what we mean by radius of convergence when we study power series. The test that we're about to introduce is probably the most useful test for convergence. If we look at something like this. Not alternating. So those tests are out of the question. Comparison tests. What are we going to compare it to? Going to be difficult. Integral test. Yeah, no thanks. Don't want to worry about having to integrate a factorial, let alone a factorial squared over a factorial. No thanks. Divergence test fails. Take this limit as n goes to infinity, you're going to get 0. Right, but that is only useful if you understand factorials. I mean, have a really deep understanding of factorials. Otherwise, you're not going to see that that limit is 0. Ratio test. Define rho to be the limit of the absolute value of a sub n plus 1 over a sub n. If that limit is less than 1, our series converges absolutely. If the limit is greater than 1, the series diverges. The limit is 1, the test fails. That means you have to try something else. So we come back over here, we look at this series. We want to look at this limit? All right, let's try and simplify. N plus 1 factorial will be n plus 1 times n factorial. Two n plus 2 factorial, 2n plus 1 times 2n plus, 2n plus 2 times 2n plus 1 times 2n factorial. Two n factorial is 1. That's nice, they're gone. Remember, if you're raising a product to a power, it's the same as the product of the powers. N factorial squared over n factorial squared is again 1. N plus 1 squared is positive. 2n plus 2 times 2n plus 1 is also positive because n is greater than 1. What is that limit? That limit is a quarter. Which is less than 1. On to infinity, yes. Our series converges absolutely by the ratio test.
From The first, like where we just set up the equation, yeah. How do we get from that, all the way at the top, yeah, to n+1 factorial squared? I'm just like trying to look at it. Wait. Oh, I'm taking this. I see it.
Good.
Yeah.
Stuff that's on top of this screen. Where did the extra stuff in denominator come from like the before stuff?
Here. What are you talking about?
Like middle left of the screen, top right of the screen, like between those steps, where did this stuff in the denominator come from?
You're talking about
Um,
here.
yeah, it's that one and the very next step, like where
So
did
from here to here.
Yeah.
Expanding 2n+2 factorial. Remember, factorial is the product of successive integers down to 1. So 2n+2 times 2n+1 times 2n factorial would be 2n+2 factorial, right? And that was just to cancel out the 2n factorial in the numerator. To n factorial over n to the 4th. And from this point, I'm just going to start writing it as the product of reciprocal.
You already know this goes to infinity because 2n grows fast. Well, 2n factorial grows faster than n to the 4th. Don't you already know this goes to infinity because 2n factorial grows faster than n to the 4th?
Well, that just means that the nth term goes to infinity, right? Which would be divergence test.
Well, yeah, but that means it's divergent.
Right. But I want to use ratio test. Right, there's more than one way to do this, right? You could use divergence test immediately. It's 2 times n+1. Right, you place the n with n+1. So you distribute the 2 through and you get 2n+2. Right. Right, it's the same thing up here, except I just skipped that intermediate step and went right to distributing the 2 through. Right, rewrite 2n+2 factorial. So we can drop out the 2n factorials. We're going to be left with in the numerator 2n+2 times 2n+1. Nothing we do with n to the 4th over n+1 to the 4th. However, we do know that this is going to be positive. Because the limit that we're looking at is an+1 over an. Right, when you divide fractions, You multiply by the reciprocal of the denominator. What is this limit? How'd you get 1? Is it n to the 4th in the numerator? It's n to the 6th in the numerator. Because you have 2n plus 2 times 2n plus 1 times n to the 4th. That'd be 4n to the 6th in the numerator. Which makes this limit infinite. Last time I checked, an infinitely large number is larger than 1. So this diverges. So it diverges by ratio test. N cubed over log of 2 raised to the nth power. So we set up our limit. Nothing we can do with the n plus 1 cubed or n cubed. But log of 2 to the n over log of 2 to the n plus 1, we can simplify. Becomes 1 over log 2. And actually, I don't even need the absolute values. Because that'll always be positive. What is that limit?
1 over log 2.
Hope we all agree that's not equal to 1. So that's good. Means the test is going to give us a conclusive answer. Is that less than 1 or greater than 1? Oh, let's not use calculators. So we have a less than 1. We have a greater than 1. You're just playing devil's advocate. Oh, I said no calculator. Log of 2 is less than 1. Log of 2 is less than 1. Right? 2 is less than e, and log of e is 1. So you have 1 over a number less than 1, which gives you a number larger than 1. Bless you. This diverges by ratio test. Three to the n over n factorial.
The ratio is 3 over n plus.
That's what's going to wind up happening, yeah. All right, so you set up the limit. We see it's going to be positive. So we're just going to drop the absolute values. 3 to the n plus 1 over 3 to the n is 3. N factorial over n plus 1 factorial. One over n plus 1. Again, remember n plus 1 factorial, n plus 1 times n factorial. And what is that limit? Which is most certainly less than 1. Oops. So we have convergence by the ratio test. Four to the n over n plus 2 to the n.
Convergence.
How'd you do it?
Because, well, the ratio is going to be a lot less than 1. It's going to go to 0, I think.
What is the ratio?
But I didn't really think about that. But I guess it'd be 4 over n plus 3.
Mm-mm.
Yes.
Mm-mm. be 4 times n plus 2 to the n over n plus 3 to the n plus 1. Right, because remember you have n here and n here,
Yeah.
which is not fun.
But it's still pretty clear that.
There is a better test. Remember, I said we had 2 tests left to cover. I only covered 1. Root test. Why did I use omega? Oh, I was in an odd mood. I think they use L, but use omega anyway. We're looking at the limit as n approaches infinity of the nth root of the absolute value of a sub n. Now the test is identical. If omega is less than 1, the series converges absolutely. If it's greater than 1, the series diverges. If it equals 1, the test fails. Outcome's the same. The only thing that's different is the limit that we're looking at. Test is perfect for series where the term is raised to the nth power.
So if we wanted to, it would work.
The what test?
Or not in the test, ratio test.
You could, but the limit is a lot more hideous than this limit.
Couldn't we use direct comparison?
For what?
Well, first we'd get rid of the first 2 terms, and then we'd compare to like 4/5 or something. Well, 4/5 to the n.
All to the n, right? 4/5 to the
Yeah.
n. You could do that.
The series comes up if omega equals 1. It's the test is inconclusive. Does that mean that every test will be inconclusive?
No, just this test.
Just that test. So you have to go.
So that's where you have to go somewhere else. More likely than not, if the root test is inconclusive, ratio test will also be inconclusive. So at that point, you're going to want to just avoid ratio test and go to something else. Right, so you actually bring up a good point, right? There are more than one way to determine convergence or divergence, right? Unless I specify a method, you're free to do it however you want. Right, so if you wanted to do comparison, that's perfectly fine. You just have to make sure that the proof is sufficient enough, right? And I don't think on the test I mandated a specific test to use. I think I just gave you a series and I said, go have fun. Converge or diverge and why. I think there's 3 like that. That sounds about right. So on the test, you're gonna have 3 series you're gonna have to test for convergence or divergence. The other two have to do with power series. This is the limit we're looking at. Well, we can immediately remove the absolute value. We know it's going to be positive. We could also just do the property that lets us pull an exponent out of the absolute value. Wait. No, that wouldn't necessarily work. -3 cubed and 3 cubed are not the same. Yeah, you would have to recognize this is completely positive, and that would allow us to drop the absolute values. I was right the first time. Forgot taking the absolute value. -3 cubed. Absolute value of that is the same as 3 cubed. We can now write this. And again, only because we know that 4 over n plus 2 is always positive. Right? Otherwise, there'd be absolute values in there. Right? Square root of x squared, absolute value of x. Square root of, or fourth root of x to the fourth would be absolute value of x. Odd powers, you don't need the absolute values. And what is that limit? Which is less than 1. Series converges absolutely by the root test. Be able to see where this is going.
Divergence.
It's going to give us the limit of n over n plus 1. What's that limit?
1.
That face.
But it does that for
It is going to diverge, but not from
yeah.
this. The test fails. That means we have to try something else. Next step is try divergence test. And hope that gives us an answer. If it doesn't, then we're really gonna have to figure something out. How are we gonna take this limit?
Is it 1/e?
How'd you get it?
Because I've seen it before.
Okay, well, that's not good enough. I want to see work. Take that as e to the log of n over n plus 1 to the nth power. Well, it's logarithms. You can write that as n log of n over n plus 1. You could also split that log if you were so inclined. As n log n minus n log of n plus 1. Ultimately a question of, actually, you know what? I'm going to wind up doing that later. Well, E is continuous everywhere. So we can essentially factor E out of the limit, so to speak. All right, this is the composite function theorem. All we have to look at is that limit. N is the same as 1 over n. That limit's 0 over 0. If you plug in infinity. Plug in. Perfect. L'Hopital's rule. Before that, I'm going to rewrite my log. Because I do not feel like doing quotient rule. to do it again. No, not according to this. I see what I have to do. Oh, that's a pain. You have to write that as a single fraction. N plus 1 minus n all over n times n plus 1 gives you 1 over n times n plus 1. So we can write it this way. And that limit is what? What is it? A limit is e to the minus 1. Which is not 0. Yay. Means I'm not going to have to worry about doing some hideous test. A series diverges by the divergence test. Here's how I typically tackle these problems. First thing I try is ratio or root test. Vast majority of the time, one of these two is going to give you a conclusive answer. If that fails, try the divergence test. Again, vast majority of the time, if ratio root test fails, divergence test gives you an answer. In the off chance that divergence test also fails, that's when you cry. Because then you have to do one of the others. Right, I'll typically try to do one of the comparison tests, unless it's alternating. Like the very last test I'll do is integral test. Let's put positive. I'm just gonna put positive. And so if the series is positive, right, you have two options, comparison or integral. If the series is alternating, you can either use alternating series test, or check for absolute convergence. I can tell you right now, if it is alternating, the divergence test fails, it's going to converge by the alternating series test. That's almost certain. Questions on the ratio root tests? This is where it's fun because now you have all of them. You just get a random series, you have to actually look at it. Said follow this flow chart. That usually works for me. Do it long enough, you're gonna be able to just look at the series and immediately know which test is your best choice. Right. If you look at this with enough time, you're going to be able to look and see that the root test is going to fail. So you then just jump right into divergence test. Hope that works. Guess you're particularly unlucky. You're going to try every single test before you find one that works. That would suck. Right. The actual tests are not difficult. It's trying to actually figure out which test to use. Right, that's what's going to be difficult and take you a long time. Next thing we study, like I said, is power series. Every single function can be represented as a power series. In fact, for the longest time, if you actually pick up an old calculus book, talking about 60s or older, you'll find that the first chapter is not limits. First chapter is power series. Something like sine. They would represent sine of x as its power series and then take the derivative. And then recognize, oh, look, the derivative is the power series for cosine. Therefore, the derivative of sine is cosine. Yeah, we don't do that anymore because we have a better way of proving that the derivative of sine is cosine. But they didn't want to have to deal with, you know, limit of sine of x plus h minus sine of x over h as h goes to 0. So they just do it as its power series. Same thing with e to the x. And a lot of the more complicated functions, they'd write it as its power series and then differentiate the power series. If you have to move on to differential equations, engineering majors, yes, sorry, you're going to take differential. Well, you'll take MEA, but it's got differential equations in it. One of the techniques of solving differential equations, specifically differential equations with non-constant coefficients, is a power series solution. Oh. Look how fun that is. When I took it, I had one problem that took me about an hour. It was like 10 pages of work. And that was just one problem. Yeah, it's fun. So you're gonna take differential equations, power series, very important. And of course, it's not enough just to get the power series solutions. You also need its interval of convergence, which means you need to know the tests for convergence, right? And we cover all of that next. How magnanimous am I feeling? Aside from the rain, nice day out. I've been cooped up in my office all day. Magnanimous am I feeling? I'd say pretty magnanimous. I'm gonna get out of here early. Test and then we're quiz and then we're done. Speaking of quizzes, 15, I think it was. The one with sequences. Yeah, that was a lot harder than I intended it to be, so I just threw it out. There's C on the canvas, it just said there's. Possibly. I mean, you can ask, but I'll answer these. Good, there's actually only one person in both of my Calc 2 classes got the quiz right. Quiz 15.